Thank you very much. Good morning, everyone. Technically, actually, good noon. Not even good afternoon or good morning. Good noon time. Good. So, what we did last time, we just discovered, well, it's not discovered, we just discussed the behavior, the ID characteristic of the MOSFET for two conditions or two zones. There is the, what you call the triode zone. Okay, is it working now or something? A second. Let's see. Let's see. Just want to make sure. Okay, good. So that's fine. So the board is fine. Good. So let's see. Let's see. 1 second. Before. Let's see. Just a second here. Okay, let's see. So yeah, okay. So that's fine. Anyways, Rose doesn't show here. So we said that the ID characteristic of a typical MOSFET, and this one especially NMOS. Because so far we were discussing the N-channel MOSFET. Alright? Because still we have another channel. Why? Because the channel is built up of N charges, which are electrons. We have also a channel that's built out of P carriers, which are the holes. Okay, so remember this, very important. So we said that the ID characteristic of NMOS typically has two regions, the triode region, where we have VDS is less than the overdrive. Below the overdrive, we have the triode region. It has its own equation. It's quadratic, means that the VDS has a degree of 2, maximum degree. Of course, there's a VDS also, power 1 here, when we multiply. So it has a quadratic feature, it shows here in the curve. Okay, and as soon as VDS reaches the overdrive, a new region, a new mechanism start in the ID characteristic of the NMOS, which is the saturation region. We call the boundary between the two VD sat. Good. And what did we say again? Something maybe we did not mention before. If you take this equation for the triode, remember that we did actually study the case when we have VDS small. And we mean by that it's actually VDS close to 0. So here we found out that there is a linear relationship between ID and VDS. And from there we got the resistance, yes or no, which is variable dependent on the overdrive voltage. That's number one. We come back to that in a second. The other one is, we cannot discuss this behavior of ID VDS if we don't have the condition of VGS is above VT. If we don't have a channel, we don't have any current. Okay? So this is condition number 1. It goes without mentioning. Okay? Without mentioning. If VGS is less than VT, we don't discuss about anything. There's nothing. There's no current whatsoever. This current happens only, the behavior of this current happens only when the overdrive is positive, basically, or VGS above VT. This is just a recap. Okay, good. Alright. So, back to the point that I just mentioned. So here is quadratic, but here in this region should be linear. How come? So to find the same exact equation before, what you did basically, you say VDS is small, yes or no? So basically VDS square close to this region will be neglected because it's small. Something that's small, if it's square, it will be even smaller, yes or no? Yes. So in that case we can say, or we can say that one, or we can say that VDS compared to the overdrive is extremely small, so I can ignore this. As soon as you do that, you find the linear relationship between the ID and VDS, the same one that we studied before, okay? Which is mu NCox, which is Kn. Kn or Kn prime? This one? This term? Kn, exactly. Exactly. And when you multiply Kn with W over L, you get Kn prime, okay? Fine. Then multiply the overdrive times VDS. And that's exactly the same equation that we studied at the very beginning of the MOSFET. So everything is consistent. That's number 1. Number 2, that this equation, they satisfy the same point at the saturation, VDS sat. Because this equation starts here, and this equation finishes here. So they must meet at this point. Means they will be same at this point. So when you replace VDS with VD sat, here or there is going to be the same. In fact, look, if V over VDS is half is equal to V over drive minus half of VD over drive would be V over drive half. Yes or no? Times V over drive would be half V over drive square, which is exactly this one. Did you get that? Yes. So that's what it means. Okay. Very quick and brief, you know, fresh, refreshing. Okay, good. So let's keep going. So today, inshallah, we will. Yeah. So this smart board is not smart anymore. It's not smart anymore. Okay, let's see. Okay. All right. So let's see. Let's go. All right. So today we study the fact. We continue the study basically of the previous one. What we said again. Here today, what we are going to study is actually further discussion of what we did before. But here, just we're discussing how the channel behaves and what will happen really when VDS is above V over drive. Basically, we concentrate on saturation region. So we said that basically before VDS above the over drive, we found that the shape of the channel here looks trapezoidal. Means that the channel basically, if I draw it, it is actually almost like it's trapezoid. So basically like this. It has big base and small base. Small base close to the drain, big base close to the source. And why is that? Because the voltage now, when the VDS is above the overdrive, is basically the channel voltage will feel the voltage of the drain compared to the source. Will feel VDS will be able to actually influence the voltage of the channel, and of course the charge will be dependent on the voltage across it. Okay, so that's what it is. So the voltage at this point, so here the total voltage here at this is actually the total overdrive, but here the voltage of the channel is not overdrive, it's actually the overdrive minus VDS. Okay, so you get eaten a bit. Okay, so in other words, basically here the voltage that will create the channel here, will keep it up, is actually VJD, is actually this voltage, because that's the voltage between the gate in here and the channel. Is actually VJD, which is equal to what? Is equal to VT plus the overdrive minus VDS. And to get this, actually go to the previous slides, we discussed that already. It's actually VJD, we did it last time. Fortunately, it's not responding very well, otherwise I would have shown you. So remember, if you check the previous slide, we found already that VJD is equal to VT plus V overdrive plus minus VDS. Now, for the case of VDS above V overdrive, look at this. VDS above or bigger than the overdrive. That means this one is going to be negative. Excellent. So in that case, if this is negative, VJD will be what? Will be bigger than VT or less than VT? Less than VT. That's it. So that means that the effective voltage here across the channel will be what? Will be negative. Is actually VJD is actually VGS, but on this side. Okay? So that means here the channel will disappear, because we said that if VGS less than VT, there's no channel. Okay? So the representative voltage here at this channel is actually VJD, and VJD here in this case, if VDS is above V overdrive, that means here the channel will basically disappear. There's no voltage that can create a channel here. Why? Because the voltage across the channel, VGS, in this case VJD, is actually negative. And in this case, is not able to create a channel. So that means the channel will disappear from here. That's it. Okay? So that's what will happen, what we get. That's what we call the pinch off. Pinch off basically is like you take a hose and then you squeeze it, squish it, until no water will go through. So it's similar to that. However, there is a current in this case, but there is no channel. Okay? There is no channel, but there is current. So that's what happens. Now the channel will stop from being trapezoidal and start to become what? Triangular. And the channel will basically shrink in the length based on VDS, on the drain voltage. If you increase it further, the channel will go shorter and shorter. Okay? But the base here stays the same because V overdrive here at this position, it gets the same, okay? It doesn't get influenced by the plane anymore, okay? That's it. So this is basically just to explain what's going on in the channel when VDS is above V overdrive. I wish. Okay, let's see. This board is really crazy. Alright. Anyway, so let's keep going. If you have any question, please stop, okay? Alright, an example, why not? Sure. So let's have a look here. So in this example, what we have, let's consider an NMOS. We know what's an NMOS, okay? It's an NMOS process technology because at the beginning of this technology, we used to have either an NMOS technology, means NMOS transistors, or PMOS transistors. Later on, we combine them to have a CMOS. We'll talk about that today too. So let's say we have an NMOS process technology, means factory develop this, fabricate this, with minimum length equal to 0.4 micron. And that's basically the name of that technology. When we name this technology, we call it NMOS 0.4 micron. We know that the minimum length is 0.4. Okay, that's it. So it shows us how much we can shrink. If the length shrinks further, we can even integrate more. So that's the naming of the technology. Okay, good. TOX, we know what's TOX. It has an 8 nanometer. Mobility is given. BT is given. Good. Now the question: find COX and KN prime. How we found it? Quickly, we go it on the fly. Yes, Mahmoud.
Using the equation.
So COX is equal to epsilon ox over TOX. TOX is given, yes or no? And epsilon ox, it has to be given. It's here, it's constant. Yeah. And it's equal to 3.45 10 power minus 11 farad over meter. Make sure the units are okay, yeah? If you use meter, you use it everywhere. If centimeter, use it everywhere, okay? Make sure that. Good. So this is simple. It's application, numerical application. Yeah. Correct? Good. So Kn prime is equal to what? Let's try to remember that. It's like CO. Okay. COX. Let me calculate while you are thinking. Okay. Think about it while I'm calculating. So Kn prime is equal to what? Mu n. Okay. So Kn prime is equal to mu n COX. So no. COX we just calculated. So multiply by mu n and bingo.
Multiply W over L because.
La, is it Kn prime or Kn?
Kn prime.
Oh, okay. Yeah. W over L. Yes, that's right. Yeah. Kn prime, it has the W over L. Yes, that's right. So the original one is actually Kn. That's right.
Professor,
I think
in the slides it is shown Kn equals. Kn is the opposite of Kn prime.
What's that?
Slide number 23.
Slide number 23. Let's see. Okay. Which one?
W over L is Kn.
Is forward or backward? You mean this one? Or before?
Yeah. It's
That's
week 1 of class 8.
Let's see.
This is 26, 25,
Let's see.
24, and 23.
Yeah, there.
Yeah, okay. Kn. So it's Kn that has the W over L. It's not Kn prime.
Yes.
Yeah, Kn. So Kn prime is actually this one. Yes or no? So this is Kn prime. So we started with Kn prime, and when we multiply by W over L, we get Kn. Okay? That's good. Thanks for the reminder. That's worth noting. Okay, so Kn prime is then done deal then in this case. Yes or no? So we just multiply COX that we just found by the mobility. That's it. So let's get rid of this. Okay. Alright. Good. Alright, so that's it. So this then we can apply. That's not big deal, okay? Okay, for a MOSFET with W over L is equal to this. So basically, this ratio means that W is equal to 8 micron, L is actually 0.8 micron, okay? Calculate the values of overdrive voltage, VGS, and VDS min, okay, needed to operate the transistor, the saturation region with DC current is equal to this. So it's given here. So we want So we have two informations here. We have the value of the current, that's number one, and we know the saturation region. Because to solve problems of MOSFET, we need to know where the MOSFET is working. Because if we know where it's working, we can use the right equation, yes or no? We cannot solve without knowing that. Alright, good. So saturation, you know which equation is actually. So IB in this case is equal to what? So we can say is Kn only.
Yeah, okay.
Makes sense? V over line square, yes or no? Yes or no? So this is the equation that we need to use. Okay, good. So this is given, yes or no? IB. Good. Kn we just calculated. And what we need is the overdrive. Stop deal. Yes or no? That's the first thing they ask. Okay? So it's easy to find. Yes or no? You find any difficulty here? Ali? Got it? So basically the overdrive will be square root of 2IB there over Kn. That's it. So there's nothing really complicated. Yes? So as I told you, we need to know which equation to use. So you need to know, first and foremost, and this will be until the end of this course, and forward, we need to know where the transistor is working. You understand? You need to know that. Very, very good. Okay, good. So we did that. So this VGS, what's the relationship between the overdrive and VGS?
V overdrive equal VGS minus VT.
Exactly. So here, the overdrive is actually VGS minus VT. And in this case, the overdrive, we have it, yes or no? So all what we need to do is add VT to the overdrive to get VGS. Done. Good. Excellent. Alright, then VDS min. Okay. VDS min means the minimum value needed to operate the transistor in the saturation. What's the minimum value of VDS to operate in the? Exactly. VDS min to be in the saturation. The first VDS is actually V overdrive. Yes or no? To start the saturation. Okay. So this is done deal. This is nothing but this. Equal relationship between them. Got it? So to stay in saturation, I need VDS to be at least equal to this, but not less than that. Got it? Alas, Bilal? Clear? Good. So we keep going. For the device in B, which is this equation, find values of overdrive VGS required to cause the device to operate as 1,000 ohm resistor for very small VDS. Oh, easy. Then again, good, that's fine. So if we are in very small VDS, so which equation we use? Triode or saturation? Because that's the only equation. Triode, why?
Because very small, not more than V.
Exactly, thanks. So that's, you got it? So in that case, which equation we use? We use this equation, IB is equal to, what's that? So hot is there, so there's no hot. So there is K, the overdrive, yes or no? Minus. But then, hold on a second, we are using it in deep triode. So that factor actually goes out. Okay, let's use the approximation directly. Or should we do it in both?
No,
we know that, right? So let's do it. Okay, okay, that's fine. So I will write it and then I will let it go. Okay? Half VDS times VDS. Yes or no? Yes, correct. Times there's a
Kn
multiply by W. No. Kn is Kn prime. Okay, Kn prime is Kn. Which one is the?
It's Kn.
Yeah. Because they have things. So here, in this case, so this is gone, because it's so small compared to the overdrive. So we have the overdrive, VDS, and here. Bingo. That's it. So the question is to find the overdrive. Very good. So what do we know here? We know the current. No. We have the resistor. The resistor. So from here, the resistor RDS is equal to what? Is actually the inverse of this. Yes or no? RDS is 1 over, yes or no? 1 over this. Kn V overdrive. Yes or no? Correct or no?
Yes.
Correct me if I'm wrong. So this is the resistance, the channel resistance. Now, Kn doesn't change, it's constant parameter. Yeah. As we calculated it already. We have R, So here we got this, we have this, we have this, and the question is to find overdrive. Well, thank you very much. From here I can get it. Makes sense?
We can use it to find VGS.
That's it. Once we get the overdrive, VGS is nothing but the overdrive plus VT.
Yes.
And the problem is solved. You see? Just in 5 minutes. Not even less. Yes or no? Clear? Yes, be there. It's very easy actually. You see, we said that MOSFET, low channel, has a linear relationship between ID and VD. Yes or no? In Ohm's law, if I write ID versus VD, so the constant between them is what? 1 over R. So what you do? You take this, flip it, and that's what my resistors. Yes or no? Got it?
Yeah.
That's it. That's all what I do. So I don't even need my memory. Just look at the equation. Bye bye. And as you get used to, these equations will be like in the fly. You will memorize them like nothing. You see? But practice, of course. Okay. Any question? Saraj team? Clear? Good. Let's move on. So that's the beauty of microelectronics. It just makes sense at the end. Okay. Alright. So today, inshallah, we keep going on discovering more about microelectronics. We introduce the second device, which is a PMOS channel. Here, as we did in the diode, what we do, basically we flip everything. What's N becomes P, what's P becomes N, and bingo. The rest stay the same. Yes or no? So the source and drain here, the diffusion or implantation now becomes P plus. Heavily doped with donors or acceptors?
Acceptors.
Too far from diodes. Acceptors or donors?
Acceptors.
Exactly, acceptors. Yes, absolutely. So, highly doped with acceptors, like what? Give me an example of an acceptor. Boron, for example. Yeah, this is the famous one. Tiny but very influential. On a bit of course, it has to be opposite polarity here. On an N-type semiconductor, and of course the gate, the metal connection stays the same. That's it. So here now, this is the physical one, this is the electrical one. Now, in order to create a P channel now, we need a P channel to create the connection between source and drain. Yes or no? So before, to create an N channel, what we did, we put a positive voltage. So now what we do? We have to do the opposite. We have to apply a negative voltage. See? That's it. That's all. A negative voltage in here will make the electric field goes where? Goes up. Exactly. So the electric field now of the channel is going this way. And of course, holes will be attracted. Yes or no? And the electrons will be pushed away. Very good. That's it. As you keep increasing until a certain threshold, same like an NMOS, bingo, officially, technically, we have what? We have a channel, a P channel. That's it. But here the voltage is negative. It has to be. Okay. That's it. It's just like a mirror. You're looking at the mirror, the NMOS look at the mirror, finds the peoples. That's it. And vice versa. That's it. So it's very really straightforward. There's nothing about complicated about it. Okay? So let's see. Okay, good. So now the question, what's the main difference? Of course, we just mentioned it. Okay, the voltage here applied is negative. Okay? Of course, to create that. And here the threshold voltage. Before we had the threshold voltage positive, yes or no? We have to be above that voltage, the threshold voltage that is positive. But now we have to be below what? Below a certain negative voltage. Yes or no? That's it. That's what it is. Okay? So now the threshold voltage has to be negative for the PMOS. Because we need to be more negative in the gate to create a channel.
So it's the opposite of the...
Yeah, I told you. Look at the mirror, you will see the other side. That's it. As simple as that. It's a beauty. It's amazing how this happens. But this is nature. We didn't do anything. It's just we studied it. Got it? Bilal? Clear? Very good. Ali? Yes? So that's it. Okay. So now, and the same thing to create a channel here is basically if you take it in absolute value, VGS has to be bigger in value than the threshold. That's it. Because both of them, they are negative. But in terms of magnitude, which is always positive, we take absolute value, this guy, VGS, has to be bigger than the threshold. But if you take it algebraically, like numerically, because negative, a big big negative number is less than a small negative number, yes or no? Do you understand? So that's why we have to use this to express that we're dealing here about magnitude, not the algebraic value. Okay? That's it. So it's not really a big deal. So what else? Now again, the same parameters that we used for. Now we're coming to Kn, Kn prime. Now Kp, Kp prime. Kp prime. What's that? Exactly. The only thing is the carrier. That has changed. So Kn prime now becomes mu Pc ox, and Kp is actually Kn prime, or Kp prime, which is Kp prime. Kp prime times W. That's all. That's it. That's it. So the rest is essentially the same. See? You don't have to be scared. It's simple. Good. That's it. The rest is the same story. Okay? Absolutely same story. Alright, so some history, to give you a flavor here. Initially, the MOS technology, MOSFET technology, was kicked by the PMOS. So he was the main running horse, or running camel if you want. Because here in this place, we use camels, yes or no? So was the running camel of the MOSFET industry. Was the big boy. Then, actually, the manufacturing of NMOS improved. Again, we said the holes are slower than the NMOS. So people, they were still trying to develop NMOS. It was very difficult to develop it at that time, to make it cheaper and easier. And then when the industry kicked in, when they got the critical mass, if you will, the NMOS took off and became the main horse. Okay? Okay? So PMOS was the leading one because it was simple, easy to fabricate at that time. I don't know exactly the dates, but just the overall observation. Until later on, NMOS dominated the MOSFET fabrication. Again, why they are advantageous? No, we know that, right? Their mobility, faster. The electrons goes between 2 and 4 times mobility of the electrons, 2 to 4 times mobility of the holes. That means if I do the switching, it go fast. If I do amplification, it go fast. So speed of the carrier is very important. Okay. Can somebody really tell me the mobility? How we get the mobility basically, technically speaking?
Sigma E.
I just want a simple. What does it relate?
Speed of this electric.
Speed, yeah. Speed of the carrier too.
To enter to.
Speed. Continue. No. Continue on the speed. Speed, yeah, speed. But there's an equation. Times the electric field. Thank you very much. So you see how it works? The speed, the velocity of the carrier is actually the mobility times the electric field. So it means if I put the same electric field for both holes and electrons, so who's gonna win the race? The one who has the higher mobility, the electrons. That's as simple as that. Okay? You understand? That's why we prefer them. Alright, good. Later on, I told you, a new technology came over and said, okay, thank you very much. I will use the sum of the advantages of PMOS technology with the advantages of NMOS, put them together and have a new technology. We call it complementary CMOS or complementary MOSFET technology, which basically will embed or fabricate both NMOS and PMOS on the same chip. Now we could do it. Later on you will see. We are not going to go deep into CMOS, but this is basically the history of these technologies. And basically, if you want to look at it, so basically in this technology, CMOS, we are able to basically build or fabricate an NMOS just beside the PMOS. And to avoid any cross-link between them, especially between source and drains, what we do, we put some isolation. And the best isolator are oxiders, oxides like what we have here in the gate. Okay. So typically we use thick silicon dioxide to isolate the transistors from each other. Okay. So that they don't mess up. Because as you can see, there's a diode here. What if not? So to stop any problem, put an isolator between them and that's it. So now, in the same chip, we can have both NMOS and PMOS. This is number one. Number two, if we use the same substrate, let's say it's a P-type. It's a P-type, okay? We use the same. So, P-type, I can build on it an NMOS, yes or no? But what about the PMOS? I need an N-type. For that, they invented what they call wells, which basically deep implantation, and they call them wells because they are like wells, above basically. We can put on them the PMOS. Now I can create an N well here so that I can put the PMOS. That's how it works. Okay? Now on the same chip we have both. But without an N well, I cannot put it. Okay? Because substrate is only working for only one. The other one I have to put a well. Now if it works, if I have different body here or substrate, then same story. If that body will favor one transistor, it'll be easy. The other one I have to create its own well, okay? It will be in the other case, P well. Huh? Alright, just to so this technology is really good in terms of especially power. Power consumption of this technology is extremely good. That's one thing. It's also very flexible and powerful in terms of to build digital circuits, logic basically. That's what was the and also later on, it's not only logic but also analog. But the main power is actually logic, so that's why all digital circuits now in CMOS. Okay. Of course, it's difficult. You are putting too many things. Okay. And this is basically the technology that is prevalent, means everywhere than NMOS and PMOS alone. You don't find PMOS and NMOS widely spread. Now, CMOS, both of them in the same chip. Good. So here, just a little thing. What we said is actually here, same thing. So I'm not going to spend my time here. Is basically what we did before. Here are recap. A recap is what you need to take today. But hold on a second. There's an equation here I'm hiding. Okay. Don't bother about that equation. We are not going to study it now. We'll see. So just a recap. So the equation that we need to use to find the current of the drain is two, basically, right? Two technically, because one of them is actually a result of the other one, yes or no? When VDS is too far from the overdrive, very small, we use this equation. Yes. Yes or no?
Yes.
Good, that's it. When it is a little bit far from that, then I will use the quadratic equation. Quadratic in terms between ID and VDS. That's it. And this is nothing but this, but when VDS is small, I can ignore this guy, and then boom, I am in the same equation like before. Now the second one, which is now, it's a totally different story, is the saturation when VDS is above the overdrive. Once it reaches the saturation, then in that case I use this equation, which is independent of VDS for now. And that's the equation here. When the overdrive is actually less than VDS, so VDS is way above the VDS, what will happen? Is there anything? That's the equation, the question that we are trying to, or we will try to do later on. Okay? So that's equation. There is an equation there. We'll talk about it later. Any questions so far? Last? Clear? All questions are welcome. You know that, right? There's no stupid question. Whoever claims there's a question that's stupid, he has something wrong with his mind. You see? Okay. Even if it is redundant, fine. We can remember things. Okay? Because we are humans, not machines. Very good. Excellent. All right. A little bit getting spicy. I told you before that what we have is actually the device that we have is actually 4 terminals. But usually we ignore the 4th terminal, that is the body. Okay? So typically when you look at the transistor circuits, you can find the circuit or the circuit. First of all, for this one, this is the, okay. Actually, there are more details to that. I'm not sure if I'm going to do that to you or not, but let's see. So this transistor, in this transistor, okay, you can see that the arrow, there is an arrow here. This arrow and this arrow, which are basically on the same side. What does it mean? It means that the current is going to the source. So the direction of the arrow and the symbol of the MOSFET show me the direction of the current. If I know the direction of the current, I should be able to know whether I have a PMOS or NMOS. Because what we say, in the NMOS, because we started it, the current goes from the to, so this is what? NMOS. And we know that the electrons, they go opposite to the holes, yes or no? The holes, they don't go with, somebody goes this, the other one goes the other way, yes? So in this case, if we have this arrow, in this case, to this direction, out of the source, to this direction, then in that case I'm dealing with PMOS. Huh? Good? That's it. So into the source I'm NMOS, out of the source I'm PMOS. Yes or no? And of course, the current always goes from high voltage to low voltage. From high voltage to low voltage. That means for an NMOS, here I'm using the window here, if for an NMOS, VD has to be bigger than VS. To know that this is a drain, because physically speaking, the drain and the source, they are physically the same, but electrically they are not. The drain has to be higher in voltage. So the terminal that has higher voltage automatically becomes the drain. Now if the voltage swaps or flips and the source becomes higher voltage than the drain, so also the definition will also flip. So if the drain becomes less voltage than the source, then the source becomes drain and the drain becomes source. Do you understand? So the definition of source and drain in NMOS or PMOS is based on the voltages. It's not based on the physical, because physically speaking, they are the same. They are symmetrical. It's a symmetrical device, remember? Remember, let's see. If you go back, let's go back. Okay, let's go back here. I'm not sure. Ah, here. Where's the NMOS? Oh, easy. Oops, not this one. Okay, there's the NMOS here. Physically speaking, like just talking about semiconductor, this is exactly like this. Yes or no? Same thing for PMOS. This is exactly the same. Physically, I mean, talking about material, touching. It's the same. So the only thing that defines these terminals is actually the voltages. The drain in an NMOS is higher than the source. A PMOS is the opposite. The drain has to be smaller. Do you understand? Because the current comes from the source into the drain for a PMOS. Because we are flipping everything. Do you understand? Flipping everything. And thus our brain becomes easy. We know symmetry. That's why we love symmetry. Because if we know the one part, the other one will be done deal. Yes or no? Makes sense? Do you understand? So that's the definition of the terminals. Yeah, I know your head is getting turning right now, but a little bit. Yeah, you're not going to get it at the first time, but try to imagine. Okay? So again, let's go back. Okay, let's go back. Okay, that's what I'm saying. So in black, what I define in black are NMOS. Now for the red, of course, now in the red, I'm dealing with PMOS, it will be the opposite. VS has to be bigger than VD. That's it. Of course, because the current is going from the source to the drain. Yes. That's it. Alas? As simple as that. Okay, good. Alright, let's keep going. Okay. So basically that's what we said before. This is nothing but that's what I said before, so there's nothing really. So basically what we said is written here. So that's it. So again, we are not using the fourth terminal for the PMOS and NMOS. Now the source for both that PMOS for now and I'll write here for PMOS and NMOS. The body terminal is equal to the source terminal. Means they are connected physically. We take the body and connect it to the source. Because we have a 3-terminal device.
Yes.
A 4-terminal device is another story out of the scope. It's not fundamental, it's a little bit more fundamental. Alas, understand? But for now we have to connect always, and that's also part of your project. You have to connect always the source to the body. To have these equations verified. Okay? Good? So make sure, Alright, again, characteristics. So basically we have how many zones we have? We have this zone, this line, we call it the cutoff. Why we call it cutoff? Because current is equal to 0. Why? Because VGS is less than the threshold. As soon as we boost the VGS above the threshold, we start to have the triode, yes or no? For small VDS, of course. As soon as I create VGS above VT, I have a channel. Now, the current is defined by VDS. So for small VDS, I will start with the triode. For higher VGS, I go into separation. For each reason of these two, I have the equation. As simple. Okay, got it? That's it. So these are the 3 regions we have. We don't deal with this for now. We are dealing so far with only these 2. And we have the equations. And that's it. So, yeah, okay, the pinch off here, as we said, when VJD, which plays the role of VGS, closer the drain, when it is less than VT, there's no channel, and we reach a pinch off. That's it. That's it. That's it, and the equations are very clear. So there's nothing really new about that. Any question or clear? See, the topic is not scary at all. It's really a joke. It's really a joke. So basically here, what it shows here is, as it shows the characteristics, basically how we do it in real life. So first of all, you have to create a channel through VGS. Of course here, what we are using, of course it's an NMOS line. So the source and the body here, actually, they are connected to each other. As we increase VGS above VT, we have a channel, then VDS will take over, will create the behavior, we choose which behavior of the current here. That's it. And that's what we did. Okay. That's it. The condition for the cutoff is this. And the equation for the cutoff is simply what? The cutoff region. What's the equation? It's just ID is equal to 0. And I don't have to be scared about it. The current is 0. I know the current here. I know the current here. Where's that? This is this one. This is for the slope. This is for the slope here. And for the triode is this equation. And for this equation is actually this one. For the saturation. That's it. Nothing really complicated. So let's keep going. This is what? Then not just big, that's nothing. And here basically, you know, we were talking about voltages and blah blah, etc. Here basically the relative voltages. So here to create a channel, so this is the voltage, the y-axis, and here's to basically there's no in y-axis, just to see the voltages here. So the overdrive is nothing but VGS above VT, yes or no? So let's see here. So let's say this is the source voltage is at this level. Above the source voltage by threshold, what we have? Above that we have a channel. Okay?
Yeah, VT.
So the overdrive is the voltage from the threshold up to the gate voltage. That's what we call the overdrive. That's it. And to be in triode, the VDS, the voltage of the drain has to be within this region. The voltage VDS has to be within this region, which is equal to what? It's equal to the overdrive. As soon as the drain is above the triode, boom, it goes to the saturation. Okay, that's it. That's about it. But of course, I'm not going to ask you these kind of questions in the exam. It's just here a recapitulation of what we studied so far. That's it. So here again, because the more you get familiar with the graphs, the more you understand what's going on with your device. So as I said here, so this is the triode region, okay? And you see, what you see here in dots is basically the limit between the triode and the saturation. What we said, the limit between them is the overdrive. So this graph, the first graph, corresponds to a certain overdrive that is called overdrive 1. So for that one, this is my limit. Now as soon as I increase the overdrive, the behavior of my device will be in a different overdrive at a different point. Yes or no? So from here, saturation. From there, the triode, and so on and so forth. As you increase the overdrive, so the boundary moves. Yes or no? And the curve for the triode is definitely a quadratic. Okay? A quadratic. And we have the equation for the quadratic. But the saturation, again, as you can see, there is no mention of VDS there. The saturation level here. It's only dependent, the current is constant, it's independent of VDS. Just dependent on the overdrive. So that's why it's constant. So this is basically in a nutshell what's going on. That's it. The triode and the saturation. There's nothing really simpler than this, I guess. If you want to know, for example, what's the curve of the boundary, is basically this. As you can see. So basically you are replacing in the equation of this one, VDS only, okay? so this is the boundary, which is this equation. Because we said that the boundary satisfies both the saturation equation as well as the triode equation, yes or no? And they reach the same equation. So you can see that the boundary here, the dotted one, is, you can see that ID is dependent on VDS squared. So when you plot this curve, basically you're plotting this function. That's it. Okay? That's it. So this is the curve that is separating the triode, which is the white here, and the separation that is blue. That's it. The first line, of course, is ID is equal to 0. There's nothing there, because the overdrive is negative. Okay, good. Okay. Alright, so all what we said here is just the only thing we need to add here is basically this fact. This is a very important thing. So you can see that here, who dictates the saturation? Who determines the current? It's actually the overdrive, yes or no? If I increase the overdrive, if I'm in saturation, if I increase the overdrive, I increase the current. So basically the transistor supplies me current with the control and then the control of voltage. So we can call it, it's a current source because it supplies me current, yes or no? But it's controlled by what? By a voltage. These kind of devices are known by voltage controlled current source. Voltage controlled current sources, VCCS. Okay? It means it's a current source. If my circuit needs current, I can supply him this. And I can control the current just by the voltage, that is the overdrive voltage, yes or no? But I have to be where? I have to be always in the saturation. I have to be always in this region. So if I'm in this region, my transistor is working like this, as a voltage controlled current source. It's a current source controlled by voltage, which is the overdrive voltage. Okay? Got it? That's it. So this is a very important thing. Why? Because we are going to use the amplifier there, and we are going to see it. That's why it's worth mentioning now. Okay? Because the amplifier needs really a good current source, which is in this case this transistor, and it cannot be a current source unless we are in saturation. Okay? So this is an important thing to mention. Okay? That's it. So what we have here, again, we are just trying to become familiar. Okay? So this is nothing but the equation of the current in the saturation. Okay? Okay? What you can see here, this is, first of all, always when you see a graph, look at the parameters. This is ID VGS. It's not ID VDS. You have to make sure to distinct that. So, if VGS is below VT, do we have any current? If VGS is above VT, we do have a channel. Yes or no? We do have a channel. But are we in saturation or triode? Who dictates that? We don't know. Unless we know VDS. Exactly. So, if we know VDS, we will be able to say whether we are in triode or in saturation. Exactly. So, here, basically, we are using this equation. This is the equation here. So, basically, the current here is actually in saturation because there is no mentioning of VDS in here. See? It's actually V overdrive square. Okay? So, that's why the relationship here, if I plot here this one, so that's the equation. So, if I write this in this graph, it's going to be half Kn, K prime, which is this one, okay, K prime times W overdrive, V overdrive square, which is nothing but a quadratic behavior, okay. But this starts only here, okay. So here the overdrive is equal to 0, yes or no? That's why I is equal to 0. When the overdrive increases, it increases, okay? Because this graph is of VGS. So if you want to plot this one, I have to write it half Kn VGS minus VT squared, yes or no? But I have to add a condition that if VGS is less than VT, ID is equal to 0, and then I can plot this, okay? This is really, really important. Why? Because actually, I don't want really to tell you right now about that. So let's discuss about it later on, actually. So here, as you can see, that the relationship between ID and VGS is quadratic. That means if I just increase VGS a little bit, my current will go really fast. Will go higher and higher, very, very quick. Okay. So this is what we need to take from this slide. Okay. And also, it's not linear. It's not linear relationship between ID and VGS is actually not linear fashion. So now there's a problem here. If I need an amplification, I really need a linear amplification. So here is actually not linear because if VGS change by a little bit, ID will change quadratically to that change. You know. So, but that's not good. We'll see that later on how we can linearize our amplifier. That is too early for that. Anyways, we finished today's class by discussing the model. The diode has a model. The MOSFET has a model. Any electronic device has a model. So this is the model that we have. We have the terminals, the gate, the drain, and the source. The body will not mention it anymore. Alas, we know where it's connected. And we are talking now for animals. Okay. So what we say? We say, okay, good. I use, of course, my device, the MOSFET, as an amplifier. I have to be technically in saturation. This is my first condition. So for that matter, I know how much current the drain supplying the source, how much is equal to half Kn V over drive square, or VGS minus VT square, which is this voltage. So I supply this voltage, I get this current. So I increase this voltage, the current here, and this symbol is the symbol of the current source. Whenever you see a diode shape and there is an arrow there, up or down, it's actually a current source. Okay? Because now this guy is working like current source, a VCCS, voltage controlled current source. This voltage is this guy, and the current source, voltage control is actually this one, the current source, this part is this guy. That's it. That's it. One more thing. If VDS for some reason, for now, if VDS increases, does it influence the current?
No.
So the current gets constant.
Yes.
What's the definition of the resistance? The resistance is defined as the variation of the voltage divided by the variation of the current. Yes or no?
Yes.
So if I take, say, this is ds, this is ds, so the variation of VDS, I can do that. Yes or no? My circuit can change. I can change VDS. Does the current change?
No.
Very good. So in this case, it's zero.
Zero.
Something over zero is what? It's infinite. That means I have basically no resistance between the drain and the source.
That's what.
Do you understand?
Yes.
I have no resistance. If I have this relationship, because I repeat, here the drain VDS, if I change VDS, does it change the current? No, very good. So let me calculate the resistance. The resistance is the change of the voltage divided by the change of the current. Yes or no? That's the definition. Huh? Good. So let's calculate it. So here is actually infinite. Yes or no?
Yes.
So that means I have a big resistance between the drain and the source. What do you say? If we have a big resistance, that means I have nothing. It's open circuit.
Yeah.
So that means I have no resistance between the two. Got it? Simple. Got it? That's what it is. So this is basically my model. I have absolutely no resistance. I have just a current source that is controlled by a voltage that is VGS on the other side, this voltage. And that's it, my current source. The more the VGS, the more the current. That's it. But VDS has no influence over that.
This
That's
is
that.
the saturation region, right?
Yes, of course. I have no VCCS if I don't have saturation. I have to be. This is a condition. Very good. See these nice questions are nice. Excellent. So that's the condition for that. And here we have another example. I think we can stop here. And the next term is next time. Okay, so quickly let's solve this together. Okay? I think you liked today's class. 2 examples in one shot. Too much, huh? But it's fun, anyway, seriously. Okay, let's see. Consider an NMOS transistor fabricated in 0.18 micron process. So we call it what? NMOS 0.18 micron. That's it. That is the minimum length. It can be bigger, but usually we keep it smaller because we want to make more circuits. All right, we have N, we have W, blah blah. We have COX, we have UN, we have VT, blah blah. This is given all by the manufacturer, and this is by the designer. Okay, good. So find VGS and VDS that result in mass operating at the edge of saturation. So what's the edge of the saturation? VDS is equal to VOV. Good. So the question is, so edge of saturation class, I know that we are in VDS SAT, yes or no?
Yes.
VDS SAT. I know where I am. Very good, that's number one. And the question, I have ID, very good. And I need to find VGS and VDS. Bingo. So in this, I can use my equation, under the saturation. So ID is equal to saturation of triode and the edge. Half Kn. I don't have Kn prime. Class Kn, that's it. That's it.
Okay.
So now V over prime square.
Yes.
He gave me ID, yes or no?
You can find K.
Very good. Kn, I can find it. C ox mu n over W over L. We have that. We can get it. So this is done. This is done. And the question is what? VGS. Oh, very much. We have a relation between overdrive and VGS. All what I did, this plus VT. What's VT? Is that VT? Yes. That's it. So we're done. Good. So VGS is solved. Now VDS is equal to what?
VOV.
Then that's it. This is my VOV. V overdrive because I'm at the edge. Finish. Right, Tanya? Excellent. So that's it. Good. Alright, if VGS is kept constant, so now I keep my VGS, the one that I found. And then what happened? Find VDS that results in ID is equal to 50 microamp. So bigger or less? Less than this. So technically this question, what I am? In triode, that's number one. So you have to have this, analysis. When you look at the things, you have to understand. So this is number one observation. My current is less. I'm keeping with the same overdrive because I'm keeping the same VGS. Yes or no?
Yes.
Yes? Good. So good. So this is the question. So what's the question? Oh, what's this? Okay. So this is the idea. Find VDS that result in this. So I have to use which equation? The triode. Very good. Excellent. So the triode. So the triode in this case. So I'm trying to solve this. So I use the blue again. ID. Oops. Okay. ID is equal to half.
Without
See, now you remember better than me. So Kn times what? Times V over 5 minus half VDS.
Times VDS.
Half VDS.
And just solve for VDS.
Okay, let's see. Hold on a second. Yes, exactly. So I know this equation. I have this. So I have the same overdrive, yes or no?
Yes.
And I have Kn the same.
Yeah.
And ID. Do I have it? Yes. So all what we need to do is use my math skills and find VDS. It's quadratic. I will have two values. One of them will not make sense. Why? Because it will be in contradiction. It has to drive. It has to be less than the overdrive. Do you understand?
Yes.
Did you get it?
Yes.
Because the solution for the quadratic equation give me two. Two solutions, yes or no? Yes. One of them has to make no sense. Okay? Which means it will contradict my assumptions, which is VDS has to be less than the overdrive. Okay, I'll let you do this. Enjoy that one. Okay? Alright, good. So then we have found what? That's big. Then the last one, to investigate the use of the MOSFET as a linear amplifier, let it be operating in saturation with VDS is equal to this. So I'm sure now that there is saturation, this is VDS. Find the change in ID resulting from VGS changing from 0.7 by plus 001 and minus 001. So to solve this in a very... So this is done. So I will delete this. It's fine?
Yeah.
Alas, let me delete this. I just need to write something here. Okay, good. So here, I'm sure that I'm using this equation. Yes or no? ID is equal to half Kn V over live square. Yes or no? That's what I know. Yes or no? I'm in saturation or what? He says
Yes,
that
yes, saturation, yes. Yeah.
So VDS is given, but the current doesn't depend on that. Who cares? Find the average, the change, the change in ID. What does it mean? It means the following. Delta here and delta here.
Yes.
ID doesn't change.
Doesn't.
So zero.
What's that?
That ID doesn't change. In the saturation.
Whoa.
No change.
That's the question. That's the change in ID.
Current is zero.
So,
Why there's a change in ID? Because there's a change in VGS.
Yes.
If VGS change, what does change?
ID changes.
ID change.
Not only that, the overdrive
The
change.
overdrive changes.
So first of all, remember that VGS is equal to overdrive plus VT. Yes or no?
Yes.
So if I make a delta here, I make delta here, of course, on the whole thing, this will go to zero, yes or no?
Yes.
And then delta overdrive, same as delta VGS, so I can replace here. So here when I do delta, let's do delta, okay? This is constant, okay? So let's keep going. This is math. Today you can enjoy math. This is constant, let's get it out. Half of Tm. And delta V overdrive is equal to what? Is equal to V overdrive, delta V overdrive, yes or no? And as the 2 comes down, you have to multiply this by 2.
Yes.
The fraction. Yes or no? Then 2 cancels with 2, and by 5. That's it. Kn V overdrive, delta V overdrive. What do I replace here V overdrive? I replace it with the average value. Because overdrives go by plus 001 and minus 001. That means the same overdrive that I had before. Yes or no? Khalas? So V overdrive, I have it or not?
Yes.
I have it. It's given. I found it here.
Yes.
It's kept constant. Yes or no?
Yes, yes.
So the V overdrive, I do have it. Okay? Delta V overdrive is equal to what? It's 002. Yes or no?
Yes.
Is that between? Oh, it depends. Here I am saying V overdrive change basically by how much? By the same thing, but from minus 1 to 001. So from minus 001 to plus 001.
So 002.
So 002. That's what it is. The final minus the initial. So this one is equal to 002 volt.
Then apply the equation.
That's it. And delta ID is it's going to be calculation. So that's why I told you math is beauty. You can do that in a very crude way. Basically, you can use the value of VGS minus, you calculate VGS or the overdrive that you have minus 01, you find the ID, then you go and then you calculate the ID for the overdrive plus 01, and then you subtract. Math can do it in one line. Do you understand?
Yes.
Good? Did you enjoy today's class? Fun? Sweet? Yeah, electronics like that. Good luck for the midterm. Thank you very much, sir, inshallah.